So we're going to look at optimization, and we're going to look at an example of a fenced off area and how can we find the maximum area possible for this fenced off area. So optimization is just all about finding the maximum or minimum of a scenario, and what are some of the values or what are some of the lengths or measurements to allow for this maximum area or volume, whatever we're looking at in context. So here's an enclosed area. Now this is just a diagram we're going to use. So let's just say we're going to use the existing fence, which is just this long line over here, as one side of this fenced off area, right? And we have 60 meters, take this out, 60 meters of fencing available. Okay, so we got 60 meters to fence off three sides because we're using the existing fence as one side. Alright, so we want to find the maximum possible area. Now it doesn't have to be a rectangle, it could be a square. Okay, it could be a rectangle in the other direction, it could be anything, but we want to look at the measurements that allows us to have a maximum possible area. So it's always good to draw a diagram. If you get a problem like this, it's always good to draw a diagram. So what I'll do is I'll actually have to look at the perimeter, because this over here is the perimeter of the fencing fence that we're going to apply. So we've got three sides to apply to. So let's just say if I name this side X, and this side X, and let's say this side Y. So we know that area is X times Y, because it's the area of a rectangle. And the perimeter, I'm trying to write it as P, is going to equal X plus Y, because we've got three sides. So perimeter equals 2x plus y, and we know what that is. Perimeter is 60 meters. So we've got 2x plus y equals 60. Alright, now what I could do is, obviously I want to find area, because I want to find the maximum possible area. So this function matters a lot to me. But I've got two variables in there. But what I could do is rearrange this and substitute that in there. So I can rewrite this as y equals 60 minus 2x. Sorry, my handwriting's pretty bad. And then I'll substitute that in over here. So I'll come on this side over here. I'll come into a fresh page. So we got, remember, area is equal to x times y. And we have y is equal to 60 minus 2x. This is our perimeter. I'll substitute that in for y over there. So we get area is equal to x multiplied by 60 minus 2x. Right? Now what I could do is I can expand this out. So we get 60x minus 2x squared. Now we've got a function for area. Now remember, we wanted to find the maximum possible area. So we have to differentiate this function because you're applying some calculus methods. Right? So we've got dA over dx is equal to 60 minus 4x. And remember, for max or min, dA over dx, or min, must equal 0. Right? For us to find our maximum, because the gradient must be 0. So we can write down 60 minus 4x equals 0. We can rearrange this function. We get negative 4x equals negative 60. Therefore, x equals negative 60 over negative 4. Therefore, x equals 15 meters. So we got one measurement for x. Now, since we got one, we can assume this is our maximum, because the question asks us to find the maximum area. Now, if you want to be sure, you can just use the double derivative test or gradient test or a graphical test to determine whether it's a maximum or minimum. Now, going back to my original function, that's a negative parabola. So obviously I'm going to have a maximum. That's how I determined that's a maximum, because I looked at the function, that's going to form a negative parabola. So I don't have a minimum, I have a maximum. So that's my maximum right there. That's my maximum measurement. But that's not my maximum area. That's just the measurement for x. If I substitute an x in there, that just gives me the measurement for x. Right? So I can tell that, okay, x is the measurement. So one length is x. Now I want to find my maximum area. So what I'll do is I'll substitute this into my area formula. So area was 60x minus 2x squared. So maximum area is equal to 60 times 15 minus 2 times 15 squared. We can pull out a calculator because there's some big numbers. So I can go 60 multiplied by 15 minus 2 multiplied by 15 squared. We get 450. So that's 450. I didn't give you units, so we can just write units squared. That is our maximum area. Alright, so that means if we look at our lengths over here, I'll just draw the diagram down here somewhere again, roughly. A rough drawing. Oh. Okay, so this is 15, this is 15. Now this over here was y, and y was equal to 60 minus 2x. So if I substitute 15 in there, minus 2 times 15, that's 60 minus 30, so therefore y equals 30. So this length over here is 30, and therefore my perimeter is 60 meters. Oh, actually I did have units. Oh, I forgot about that. I did have units. I said 60 meters, didn't I? So this becomes meters squared. Alright. So that's how we find an optimization problem. Now this is just a real basic problem for optimization, where we found the maximum or minimum. But as we progress, we will look at other problems where we'll be given two values and we have to actually determine which one is our maximum or minimum. Alright. But that is the kind of steps you will go through, is where you form a function. Right. You might have to substitute in something to form that function. So you have one variable. You always have to remember to differentiate, make it equal to 0, find the value for x or whatever that variable is, and then substitute that in to our original function to find the maximum area. And if you want, you can find the dimensions or lengths of the enclosed area or fenced off area based on your problem. But that is how we go through and solve an optimization problem.